Okay, so we're going to work on how to handle inclined planes, ramps in other words. So let's go shapes here and let's create ourselves an inclined plane. So boom, there it is. So we have an inclined plane, looks like this, and we have some object on the inclined plane. So we'll create a little box, boom, rotate it to match. Okay, so some things to keep in mind about this. Because the plane is inclined, dealing with the weight is going to become the weird part. Because the weight is responsible for two things. The weight is responsible for taking this thing, this object, and at least attempting to accelerate it down the ramp. So the weight is involved in pulling it down the ramp, and the weight is also involved in keeping it on the ramp. So in other words, the weight is doing this and this at the same time. And if you look at it, you can kind of see why. The weight's directed straight down. Well, that isn't just along the ramp, and it isn't just perpendicular to the ramp. So the first trick we're going to deal with is, since this thing is ultimately going to, if it's going to accelerate somewhere. Let me turn my arrow around. So if this thing's going to accelerate, I think you would agree with me that it's either going to accelerate this way, if it's being pulled or pushed up the ramp, or this way. That it really is a one-dimensional motion type situation if you consider the one dimension to be this way up and down the ramp. So I want my acceleration to be just in one dimension. So I'm going to mess around with my Cartesian coordinate system. In other words, normally, let's get a double-headed arrow here. Boom. And we'll go start and end. Boom. And this. So normally we have our x-axis and our y-axis, and they have to be perpendicular to each other. That's true. But there is no law that says the x has to be perfectly horizontal, or that the y has to be perfectly vertical. In other words, if I want, I can take these and turn them. So I can line them up, and instead of doing this, hold on, I can take this one and rotate it so that my x-axis, just kind of basically tilt my head, so that my x-axis is up and down this way, and that my y-axis is, of course, still has to be perpendicular, so that my y-axis is like this. Now, my acceleration, if there is an acceleration, and all my motion up and down the ramp will be along the x-axis. So I tilt my axis system. Now the weird part of this is what it does to the weight. The weight will now be a vector that, while it points straight down, in my new coordinate system, it doesn't point straight down along the negative y. So it's at an angle. That's a little weird. So mg turns out to be sitting out here. Let's use this. Do I have pink? Kinda. So mg turns out to have now an x and a y component. You can see them, right? So if I got for the weight, the x component would be about this big, and the y component would be about that big. It's my y component of the weight and the x component of the weight. So we're actually going to have an mg x, all right, and an mg y. The fun does not stop there, my friends, because not only are we going to have to break the weight up into two components, the reference angle, as you might have noted by looking at this, our reference angle, this angle, is not going to be the angle they give you. They always give you this. They seem to always give you this angle down here, which, by the way, if you look at it long enough, is really this angle too, right here, which is not our reference angle. We always say, we don't want to use that angle because it's a weird one. here's what the bottom line effect is. You know how normally we find the x component using the cosine and the y component using the sine? In my experience, the simplest way to handle this is to remember that this is an inclined plane. And with inclined planes and this angle, when you use this angle, just switch the roles of the sine and cosine. So, for example, I'll use W for weight. Hold on, I did not want that to happen. We're going to undo that, and we're going to go here. And I thought I said, no, I don't want that. I said save to properties. So the x component of the weight is going to be the magnitude of the weight, mg. In fact, we'll just do that. We'll write mg here. So the magnitude of the weight times the sine of the angle that they give you here, of that angle. Because that angle is actually not the reference angle, but it will be the one they give you. Now the other option, for those of you wondering, is to subtract that angle from 90 and go ahead and keep it the way it was. My experience with both ways is students do a better job going, oh, it's an inclined plane, and they know to switch the sine and cosine. That tends to work the best. So the y component of the weight is going to be mg cosine of that angle of elevation, the incline, the angle of incline, or whatever they call it. So that's some weird stuff. You got to tilt your axis system, and the weight will have components now. Normally it's all just in the y, but not now. So now we're looking at what you're seeing is this incline has only a little bit of the weight trying to pull it down the ramp, and more of the weight over here, the y component, is actually keeping it on the ramp. And by the way, would you expect the normal force to be just equal to the weight? Come on, think about it. Normal force is perpendicular. So if I pick, we'll do green, I guess. The normal force, in this case, is going to equal the y component of the weight, only that much. So there's less normal force here, too. Keep that in mind. Normal force isn't going to be straight up weight like it is if it's like on a horizontal surface. Okay. So if you just had this situation, some frictionless ramp, your net force, of course, would end up being just the x component of the weight. And it would accelerate down the ramp. But of course, if you have friction, it could be opposing that, going this way. Unless something's pulling it up the ramp, and then friction would oppose it the other way, because it always opposes motion. So, you can see, things can get complicated quickly. Let's look at a problem. So I got to pull one up here. I'm going to pause the video, and I'll be right back. Okay, so we're going to consider problem 15, the one with the motorcycle. It has a decent number of forces in it. It gives us a chance to work with this whole inclined plane thing. So, I don't know, we'll make our ramp, let's do it. Well, that's not a ramp. Get rid of that. This. I'm going to flip it though. So I'm going to go boom, boom, boom. Flip. Left, right. There it is. So here's our ramp. We're going to have a motorcycle, which I'm going to represent with a kind of a circle thing. We'll call it there's our motorcycle. And our motorcycle is going up the ramp. Not that we're going to draw the direction of the speed or anything, but it's going up the ramp. So what are the forces, we look at our problem, on our motorcycle? Well, the fact that it has a mass means that it is going to have a weight. So the weight will be pulling downward, straight down. Our axes, of course, are going to be oriented like so. This will represent our y-axis, perpendicular to the surface. So I'm going to make sure I get that right. Does that look perpendicular? I think we need to move it a little bit. Yeah, that looks closer to perpendicular. And then our x-axis is going to be along the ramp, like so. So we have our weight acting downward. And it, of course, is going to have components. But for now, we just are going to write mg, weight. Now, what else do we have? Well, we're going to have a normal force that I suspect is going to be equal to the y component of that weight. Then, oh, by the way, let's not forget this is a ramp that is inclined at 30 degrees. So they say the propulsion force pushing the motorcycle up the ramp. So the force pushing it up the ramp, we'll go call it, so let's see, force propulsion. And air resistance produces a force that is opposing that motion of 3, it doesn't matter magnitude, but we'll call it force of air resistance. So I have, and this force doesn't look horizontal enough for me, so I'm doing that. So this is my free body diagram. Well, it's kind of a lot of a diagram. Let's just draw the actual free body diagram at this point. Whoops, I got some stuff left over. Sorry about that. Okay. There we go. Get rid of this garbage. Okay, now if I'm going to draw an actual free body diagram, we'll do this. We'll say, all right, I've got my object. Boom. And the forces acting on my object would be, let's see, I've got normal force up. I've got the weight at an angle to the y-axis, right? I have a force going to the right. Now remember, right is kind of relative here. It's like to tilt my head. But I got a force propelling it up the ramp. And I have air resistance working against. So this is my free body diagram. And we'll label it real quick. So I have normal force, the propulsion force by the motorcycle, I have the weight, and I have the force of air resistance. Now I'm going to go to my component diagram. So I'm going to take this, put a dot here, and I'm going to make my component diagram, which is going to break everything up into its x and y components. Well, some of them I don't need to break up. Normal force is normal force. Can't seem to help but make 2 arrows every time I do this. We got this, right? There we go. Normal force is no big deal. In fact, we'll just do this. Clone. There we go. That propulsion force is the same, because it's all in the x. Likewise, there we go. Our force by the air resistance is the same, but weight has components. So the weight is going to have a y component and an x component that is pulling to the left as well. So we're going to need another arrow here, and it's going to look something like this. So what we have here is weight in the x, force of air resistance, weight in the y, and then the propulsion force, and of course the normal force. Well, let's work in the y dimension first, because we're going to need to figure out that normal force, and in order to figure out... Actually, wait, I don't think we do we? No, there's no friction to calculate in this one. They just kind of tell us the air resistance. So I think we have enough to go on in the x dimension. A lot of times if you have friction to work with to figure out, if the problem requires you to use the formula for friction, you would have to find this normal force first, and then in the y, then you could use it to find friction. But they just tell us air resistance right out, so that would be the closest thing to friction. So I think we're good. We can go straight to the y dimension, I believe, and sorry, the x dimension. So in the x dimension, two ways to look at net force. Net force could be the sum of all the forces. So it would be, going to the right would be the propulsion force, we'll call it positive, of the motorcycle. Against it will be the force of air resistance, and against it will be the x component of the weight. But the other way to look at net force, of course, in the x, is ma. And all the acceleration is going to take place in the x. In the y, it's just going in and out of the ramp. It's no big deal. It's not going to go anywhere. So, over here on the left, I think we have enough information to sort this out. The net force is going to equal the propulsion force, which they give me, 3350, minus the force of air resistance, which is 290. And now I need the x component of the weight. So that's going to be minus the mass, which was 338, times g, times the, careful, sine of the 30-degree angle. Because remember, if we're going to use that angle, we have to flip the sine and cosine for inclined planes, because that angle isn't actually the reference angle. So real quickly, let's figure out what that particular thing is. So I've got 338 times 9.8 times 30 sine equals. Okay, so this works out to be net force is 3350 minus 290 newtons minus 1656.2 newtons. So let's see, we're going to have, that's going to be negative, minus 290, and then plus 3350. So I'll get a net force along the ramp. Let's see, going up the ramp, because that's it's positive. We said that to the right is going to be positive. Up the ramp will be positive, so that's 1403.8 newtons. And now I can go over to the other way of looking at net force. I can take the net force, use it over here along with the mass of the motorcycle to find the acceleration. So the net force divided by the mass will give me that acceleration. So that's going to be 1403.8 newtons divided by the mass of the motorcycle, which is 338, equals the acceleration of the motorcycle. And I'm going to have 1403.8 divided by 338, bammo. I'm going to get an acceleration that is equal to 4.15 meters per second squared up the ramp. Now, is that what they were asking me for? Because I didn't even look and see. Find the magnitude of the motorcycle's acceleration. They tell me it's 4.148. I tell them I am good with that, 4.15. Yep, I'm okay. That looks like a right answer for me. So, that's an example of how to handle this. And remember, some problems you might need to work and actually work in the y dimension first and sort things out. Those two forces will be equal, the normal force and the weight in the y component of the weight. Now remember, that's going to be mg cosine of the angle of incline. You might need that in order to find normal force. because sometimes you might have to calculate friction, so be aware of that. All right, I think that's it. We will now turn our attention to Atwood machines in the next video.